Okay, so another question, kind of similar to the last one, but not exactly the same, is what would the mass in pounds of 1 cubic foot of water be using the density of water that we've had so far? Well, we've got the volume as 1 cubic foot. It would be much more convenient if we could get it in cubic centimeters. So then we could find out how many grams that is, and then we could change that to feet, or I mean pounds. So let's see, between feet and centimeters, let's see if we can find a conversion factor. Yeah, there's not a lot of feet in here. So let's see, 1 inch is 2.54 centimeters. So we could use that. Oh, no, wait a minute, there it is. So 1 foot is equal to 30.5 centimeters. So that'll make it much easier. 1 cubic foot, and there are 30.5 centimeters for every foot. But remember, these are linear feet and linear centimeters, so we need to cube that conversion factor. So now cubic feet will cancel with cubic feet, and we get cubic centimeters as the unit, but we have to cube the 30.5 when we multiply through by it. So we end up with 28,372. That's beyond the significant figures we can use, so I'm not going to write the rest of the number. 28,372 cubic centimeters for 1 cubic foot. The mass, once again, is going to be density times volume. Now that we've got the volume and the density in compatible units, we can just multiply them together. 1.00 grams per cubic centimeter times 28,372 cubic centimeters. And that would be a mass of 28,372 grams, but we wanted it in pounds. So we can take the conversion factor. 1 pound is 453.6 grams, and make sure grams is on the bottom so it cancels. And 28,372 divided by 453.6 gives us 62.5485, and I'm not going to write the rest of it, pounds. Okay, 28,372. I'm just doing this again to make sure. Right, 453.6. Yep. And that's okay. So that number is definitely more significant figures than we're allowed to use. Let's see. I changed this to 1.00, so we got 3 significant figures there. Whoops. I changed this to 1.00, so we got 3 significant figures there. We have 3 significant figures here, and nothing else that's less than that I see. So it looks like 3 it is. 62.5, the next number is a 4, so it has no effect on the numbers we're keeping. So 62.5 pounds would be the mass of 1 cubic foot of water. Okay, and another interesting example. When I say interesting, it's bad news. Okay, so say that my gas tank is completely empty. I had to push the car into the gas station to fill it up, and filling it up increases the weight of the car by 112.6 pounds. How big is my gas tank? That is how many gallons of gas did I put in the tank? And we know that the density of gas is 0.68 grams per milliliter. And of course, the obvious problem is that I'm asking for the size of the tank in gallons, and the mass of the car is given in pounds. So we have to sort of rectify the units, make the units compatible with one another. Generally, it's possible. It's easier to change linear units than it is to change compound units like grams per milliliter. So I would say change the mass of the gasoline to grams. That's the easier way. You don't have to do it this way. You could change the density of the gasoline to pounds per gallon, and then just use the numbers as they're given in the problem if you wanted to. But I think that doing it this way would probably be easier. So we'll change the weight to grams, so it'll be consistent with grams per milliliter. So 112.6 pounds, and there's 453.6 grams for every pound. Pounds will cancel, and we end up with, let's see, 112.6 times 453.6 is 51,075.36 grams. Okay, that's way beyond significant figures we're going to be allowed to use in our answer, but this is an intermediate answer, not the final answer, so you might as well keep them. Okay, so let's see, the volume of the gas would be easy enough to find in but that it will come out in milliliters. So we have volume from our triangle. Sorry. Yeah, let's try that again. Density is mass over volume. Okay, so volume would be mass over density. And the mass is 51,075.36 grams, and the density was 0.680 grams per milliliter. Grams here will cancel out, and we'll end up with milliliters on the top, and divided by 0.68, which equals 75,110.8 something milliliters. And now we need to change milliliters to gallons. The conversion factor sheet, I don't believe, for volume, I don't believe it gives anything between gallons and milliliters, but it does give gallons to liters. So let's go milliliters to liters, and then we can go to gallons. Okay, there's 1 liter for every 1,000 milliliters. So milliliters will cancel, and we'd have our density, our volume in liters here. And then to go to gallons, there is, let's see here, 1 gallon for every 3.786 liters. So that's 3.786 on the bottom there. So let's see, if we have 75,110.8 divided by 1,000 divided by 3.786. And we get 19.8 gallons, which is a reasonable size for a gas tank. And let's see, that is 3 significant figures, which is what the density was. That looks like the limiting factor for significant figures. So there we go, 19.8. For that same question, as I mentioned, there's another way we can do it. You could always change the density to pounds per gallon and do it that way. So what would it be like if we did it that way? There would probably be fewer steps doing it this way, but the math would be a little more challenging. So let's see, we have 0.680 grams per milliliter. To change this to pounds per gallon, we have to change grams to pounds and milliliters to gallons. And there is not a conversion factor in the table that will do this in one step. So we're going to have to do the 2 units separately, even though they're both in there. We're going to convert grams to pounds first, and then we can come back and convert milliliters to gallons. All right, using the conversion factor table, grams to pounds are units of mass, and 1 pound is 453.6 grams. All right, well, now we've changed the top unit to pounds. That's what we want it to be. So first half done. Now for milliliters to gallons, as we saw in the last example, there's no way to go directly from milliliters to gallons with the values on our conversion chart anyway. So we're going to have to go to liters first. But remember, when you're converting these units, milliliters is the unit you want to convert, and that's on the bottom of the fraction. So in the conversion factor, you want milliliters on top. So there are 1,000 milliliters per liter. Milliliters now cancel, and you would have pounds per liter as your unit, if you wanted that, but we don't. We want pounds per gallon. Again, this means that since the unit you want to get rid of is on the bottom, that unit has to go on the top. And it's 3.786 liters for every 1 gallon. Okay, so liters now cancel, and we end up with pounds per gallon if we multiply all that out. 0.68 divided by 453.6 equals times 1,000 equals times 3.786. And we get 5.67566. I'm going to cut it off there. Pounds per gallon for gasoline. Okay, so we've got the density. And in the problem, it said the increase in mass was 112.6 pounds. So we have the mass. What we're looking for is the volume. So looking at the triangle again, volume would be mass over density. Okay, so mass is 112.6 pounds. Divided by 5.67 blah, blah, blah pounds per gallon. Six, and it's 19.839.10241 gallons. Once again, it looks like 0.680 is the limiting factor here for significant figures. So it's going to be 19.8 because the first digit we're dropping is a 3. And so that will have no effect on the digits before it. So 19.8 gallons is our answer from this method. And lo and behold, that was the answer from the next method. Or from the last method. So you can do it either way you want. It's up to you. Either way is perfectly correct. And there are other ways to do it that are correct also. So the choice is up to you, whichever way makes more sense. Like I said, fewer steps doing it this way, but the math is a little harder because you have to convert 2 units, one on the top and one on the bottom. Okay, so that's actually all I had to do for today. We're coming rapidly to the end of the math section. So we'll see what I can come up with for the next lecture. Actually, I'm going to cut this lecture even shorter than I have been lately. And so I guess I'll see you next time.